the proof of the Grothendieck conjecture, and usually the last piece in mathematics is, you should explain everything. The last piece in music is usually presto or something like that, but I will be going very slow today, so this is an andante. We're going to prove the Grothendieck conjecture, and my strategy will be that I prove for you the Grothendieck conjecture in what we call the unpolarized case, so just for p-divisible groups. And then there's an analog of that for principally polarized case. And for the principally polarized case, I will give indications of the proof, but to write out all the notations will really be very puzzling, and I will show it to you in two explicit examples how to do it, and then you immediately see how to generalize that. And I want to mention, and I'll discuss that amply, that if you do the analog for polarized Rashad-Day groups or polarized abelian varieties where the degree of the polarization can be divisible by p, there's no chance that this generality holds. And I gave you an example already, and I'll discuss a little bit on that and give you a conjecture. And then I'll end with an analysis of the second proof of the Mani conjecture. I need, in my indications of the principally polarized case, I need something on this place for principally polarized abelian varieties and for principally polarized p-divisible groups. So if you take the notation of last time and you plug this in, then you get also the principally polarized case. So in the principally polarized, in the polarized case, you in any case have G base vectors not in VM and G base vectors in GM, and you write out the display as it is, and then for convenience we renumber the indices in this way, and moreover you make the basis what they call a symplectic base. Now there's always a confusion. Sometimes the symplectic base goes from the first vector pairs to the last vector, and in this notation the first vector of the x's pairs with the first vector of the y's. That's easy because then you get symmetric matrices and then you get exactly the analog of Riemann symmetry conditions. So on that you have these Riemann symmetry conditions, and if you plug in these variables in the Newton polygon diagram, then G of them are on the vertical line. The remaining ones are either left or right, and the right and left ones are symmetric in the sense that they're equal. So that's the symmetry condition, and that gives you the deformation space. Now if you want to do this in a non-principally polarized case, in the paper by Norman and myself there is a very concrete description of it. You have to take care that you're choosing the x's and the y's, that the pairing may involve factors p, but that the factors p go up. And that's tricky to do, and the consequences are much more difficult, and certainly this is not true in general in a non-principally polarized case. In a non-principally polarized case, the moduli space is much more complicated if the degree of the polarization is divisible by p, and it depends on psi. Because, for example, you've seen in Ching Li's lecture the Certate coordinates, and they behave perfectly well also in the arbitrary polarized case. But in the lower p ranks, it is completely different. So that's what I want to say about this, and I won't say much about this. This is just notation, and I hope you have copied it if necessary. I'm sorry it's not in the notes. Okay, so that's that. And before I go to the Grothendieck proof and the proof of it, I want to make one remark. In the notes, it says not for publication. We hurried really to get them ready before this is cool. And there is a little omission, namely in some parts I use the Newton polygon for f, and sometimes I use the Newton polygon for v. So if you're puzzled about sometimes the use of the Newton polygon, that's certainly my fault in the sense that I have taken from different sources and not being well aware that sometimes it's notation should be slightly different. So just a matter of notation, but of course good mathematics really uses good notation. So be careful, and in the final version we will certainly correct this. Here I give an indication of how we prove the Grothendieck conjecture. So let's go over this very rapidly, and then I'm going to indicate you details. So what we did yesterday was that this catalog of p-divisible groups, or this moduli space of isogenies of a certain degree, is irreducible, right? And that was really the key fact. That involved the nasty computation, and it involved the general theorem on purity of multi-polygon strata in any family of p-divisible groups. And from this, of course, you prove 7-1. 7-1 is the deformation to A at most 1 in the case x0 is simple, right? Because the case where A is 1 on this catalog is dense, and as it is irreducible, every point is in the boundary. Now I use the word catalog. Catalog is a concept which I introduced for this thing, and you see, if you want, what is a catalog for a certain set of objects? It's a base space, it's a family over it, so that every small animal in your zoo appears at least once in the fibers. But it's not a representable function. I mean, if you take a surjective map to the base and you pull back, again, it's a catalog. So this is a catalog, so this T is a catalog of all p-divisible groups isogenous to this GMN over an algebraically closed field, and every fiber appears at least once, and that's this little lemma that you always have for any X you have a isogeny of degree R. Okay, so this was the basic tool, and from here things are going much more smoothly. So then we prove 7-1 for x0 simple. I will show you that there exists a filtration on such p-divisible groups during the name modules, and certain displays I will put in normal form, and I'll explain all this. And these three things imply the fact that any p-divisible group, no polarization, any p-divisible group can deformed to an A at most. One case, keeping the polygon fixed, right? So the 7-1 is the step where from the singularity perhaps you move out to the space where the A is at most 1. Then we did Cayley-Hamilton, and Cayley-Hamilton said that if you are at the point at A equal 1, then you really have smooth deformation spaces to all Newton polygon strata below the given one, and that was 5-8. And then there's a little proposition, 8-5, and I'll comment on that. I'll give you two different proofs of that. That if you take a sequence of two specializations, then it implies that this one can specialize to something which is here. And that's 128, and that's the Grothendieck conjecture. And at the same time, we prove the following. You take any divisible group, and you suppose it's nutribolic as something, it's perhaps beta, and you take a gamma, which is below beta, below or equal, and you compute the dimension of the space where gamma is realized. Right now, of course, this dimension of the whole closed set is the same as the one where you leave out the lower dimensional thing. So this dimension is equal to the dimension of the interior, but that we proved by Cayley-Hamilton to be equal to the dimension of gamma. And I remind you that the dimension of gamma is just counting points in a certain region. The region was, so you have this parallelogram, you have this is gamma, And then you take all lattice points, perhaps on your Newton polygon, but strictly below these two lines. So this area, only the integral points are baptized parallelogram of gamma, and the dimension of gamma is just the combinatorial invariant number of lattice points in this region. So the computation of the right-hand side is completely easy. I mean, whenever you give this to any child or adult or whoever, but doesn't need to know any mathematics, counting these points is just easy. I gave example in my notes, and then it's extremely easy. So the right-hand side is a purely combinatorial thing, and left-hand side is something which is really important. Now, I like to make, before starting technique, I like to make one remark which applies here and which applies in the principally polarized case. You see, this big psi is the ring which, if you take the formal spectrum, you take the completion of this point. But mind that I really write equality there, and I should write equality also in that big formula, because it's kind of canonical. So you really have coordinates on your locus, where the A number is 1, around every point, given by lattice points in this region. And the proof just does it for you. And if you want to go up with your Newton polygon, you should write the equations. And what are the equations? Well, you take all the points which you miss in your new Newton polygon, and you equate those equations to 0, those coordinates to 0, and you get a new one. So around every point you have a coordinate system. And I must confess, I've never understood these coordinates. In the sense that if you have set date coordinates, really know exactly what they are, and we can really feel them, right? But these coordinates, I have no idea. I mean, I can prove that that formula is correct, and that that identification is, well, canonical, doesn't depend on any choices. But what is the explanation of these coordinates? And I think there should be a much better proof of the whole theory than what I gave here. And I don't know. And the reason why I'm very interested is in all these cases, the Newton polygon stratum is stratified, is foliated in two directions. And one is central leaves and the other is azartony leaves. And the central leaves, I can compute the dimension as a subspace of this parallelogram. So the obvious question is the dimension of this leaf not only given by this smaller region, but are the coordinates along the leaf exactly the coordinates parametrized by these lattice points? And I've really worked hard on it for months, and I wrote out many examples, and there's no proof for it. So I'm doing something completely too low in theory, and one really should find a much better proof. Okay, but this is something completely outside what is being done here. So now let me start the proof. So you know the layout, and I won't concentrate on most things, but I will say something about the filtration. I'll describe the normal form, and I'll describe this 8.5. And so that's what I'm going to do today on this part. Now, question, is this scheme, is this clear to you? Or should I repeat any of the statements, or what do you like? I mean, I really like to understand that you see the technique working, and what are the steps. Okay, if not, then I will comment on a few things. One of the interesting and beautiful tools in studying p-divisible groups is making filtrations. A p-divisible group has a Newton polygon, and you can ask, Suppose I give you one of the slopes in my Newton polygon. Does there exist a sub-p-divisible group which has this slope? Now, over a perfect field, this is okay, because this p-divisible group is isogynous to a product of GMN, right? So you take the appropriate GMNs for that slope, you map it into, and you get a sub. But over a non-perfect field, it's not true that any isoclinic part does appear as a sub. And you've seen that already in Xing Li's lecture. If you have certate coordinates, the mu p sits in the kernel, and the z mod p sits in the co-kernel, but there's no way to push this around over a non-perfect field, and you know that. Proof, take the universal deformation of an ordinary elliptic curve. That is defined over some formal, over the spectrum of some formal ring. Does this have an infinite amount of p-power torsion? No, of course, because that would really imply that that any point over a finite field has an infinite amount of p-power torsion points, and that's not true. So the p-power torsion points are in the co-kernel, and to lift this back to your p-divisible group, you really need a covering, and those are the so-called Ikusa curves. So the Ikusa curves are those curves over the modular space where you can lift back the étal part of your p-divisible group back to your p-divisible group. And that really needs a tower. And that tower is infinite if you do it over the whole modular space. So what I want to say that over a non-perfect field, this non-splitting of this exact sequence is really, from every point of view, it's very intrinsic. I mean, it's clear from arithmetic point of view, it's clear from geometric point of view, and the same holds for all slope parts in this case. But Grothendieck conjectured long ago that there does exist a slope filtration in the sense that the biggest slope is a sub 1, then if you divide by that, you can repeat that process. And that was proved in a beautiful paper by Zink, I think it's 102 in our references. And to have this over an arbitrary base, Zink did part of the theorem, and in a joint paper, Zink and I made further contributions. So that's what we did. Now today, I'm not going slope filtration, but I'm going a much finer invariant, which I call a maximal filtration. So what's a maximal filtration? Everything is in the notes. A maximal filtration is a filtration of your p-divisible group, such that taking the quotient by any step, again is a p-divisible group, and such that every subquotient, so you take a step and the one smaller, you take the quotient, is a simple abelian variety, right? And that certainly does not exist in general over non-algebraically closed fields, but it does exist over algebraically closed fields, and so that's a filtration. Now what I do, I'm not going to write it out. I first take such a filtration, right? And I'm going to write down a deformation of it, keeping the filtration. And later I will give you an example to show you how that choice really makes a choice in the modular space in which direction to move. It's beautiful, really. So I make a filtration and I look to the deformation space of x0 plus the filtration. So the filtration extends to your whole deformation space, right? Okay, so that I can do. And now what I do in the part where I have an isoclinic part, I can really, well, first in the case where I have one simple part, I can really apply this one. So I can make a deformation where on all simple parts, the A number is 1. Okay, so now suppose I've already done that thing. And let's suppose I have only, so example, only 2 simple parts. Yeah, so my p-divisible group is just an extension of 2 simple p-divisible groups, right? Then I can take a filtration, and I've already done my deformation in such a way that on the simple parts, the A number is 1. And let's write out a display for that part. So let me put little crosses here. This, and this is just the deformation space of the smallest part, right? And for the smallest part, the A number is 1. Now, there is a lemma which says normal forms, which says that if you have a DNA module whose A number is 1, then you can write the display in the following form: zeros on the main diagonal, ones here, P here, and this I don't know, and there's only one here. So lemma, and that's the lemma 511, give any p-divisible group where the A number is 1 and which is local. Suppose then there does exist a choice of base such that on that base the display is a normal form. A normal form says that in the left-hand side you only have ones here, you have 1 here, the rest is 0. Here is some complete mystery, and here you have just p's and zeros elsewhere. Now, I'm sure, I mean, you're such a good audience. I'm sure that most of you can do this immediately as an exercise. Of course, what you have to do, you take the A number is 1, and it's local. So the DNA module is generated by 1 element. Okay, take that 1 element as first base vector. Then take the f of that as the second base vector, right? And then you go on. So that means that if I apply f to the first base vector, I get a second. If I apply f to the second base vector, I get a third, and so on, right? Now, you will see that if you do this process, as long as you're out of VM, you can really do that. But on VM, f maps that thing to something which is in PM. So you can, on the VM, you can take again the image, mod P, but then here you have something which is P times the old vectors. So this box here is completely mysterious, but the rest is like this, right? Now I've chosen this one so that these are normal forms, right? So here's a 1, here's a 1, on diagonal I have 0, on diagonal I have 0, here I have 1, here I have 1, and here I have 1, and the rest left to this axis, everything else is 0. Yeah? So if not indicated, the rest is 0. Yeah? Now I must multiply with some matrix to get a deformation. Now, what I do is I choose the following matrix. Where's my? I'm almost sure to know what to do. But let's make clear. Yes. Again, I have this matrix, and I take a variable s in the left-hand upper corner of this matrix, and the rest is 0. Yeah? So please remember, how do I get deformations? You just take the original display, you multiply by a rectangular matrix. In the rectangular matrix, you may choose anything in some base rings, so for example, variables, right? Then I take this left-hand upper corner to be equal to a variable, and the rest I just equate 0, right? Now if you multiply, so the deformation space, right, was given by A plus TC B, and then here I have this is C, and here I have PB plus TD, and here I have D. So the displayed form was this. Now I don't care what I have here. here there's all kind of garbage. I mean, here's a lot, this multiplies with this, and that adds to the thing here. So what I have here, I'm not very much interested. But I'm very much interested what happens in the left-hand upper corner, right? And now it's clear what you get, namely if you get this multiplication, right, it's clear that the only thing you add is an S here. Yeah? Just look, I mean, you multiply this with matrix, right? And this one is much too early, so this one doesn't help at all. This one does help, because only in this row and this column, if you multiply, you get S times 1, that's exactly here. Right? Now, here I have a square I have this matrix, and the A number is given by taking the DNA module, mod out by F, mod out by V, and then see what the dimension is. And you easily see that if you take this matrix, you reduce mod P, that's what they call the Hasselbalch matrix. This is the action of F on M mod Vm. So this matrix mod P, so this mod P is the Hasselbalch matrix, is the action of F on M mod Vm. Right? And so now I'm done, because I really want to divide out M by Vm and M by Fm, take the quotient, and compute the dimension. But this matrix has rank 1 less than it could have. So this now has A number equal to 1. So my claim is, in this case, I do have again a deformation of filtered groups. You see, I didn't change anything in these boxes. Right? There are no variables here, there are no variables here. So that box really remains the same. So that sub-p divisible group remains a sub-p divisible group. Only the extension I change in such a way that beforehand the extension made that the two A's, the two alpha p's, really appeared in the NSP divisible group. But now I get a non-trivial extension of these two alpha p's, and only one survives, and the other is not an alpha p anymore, but sitting on top of an alpha p. Okay, so this is the end of the proof of set 1. Up to that you really have to sit down and write out all the formal details of this. But certainly I think that's not very helpful to dazzle you as all the formulas and so on and so on. Right? Okay, now, once I have 7.1 and I have 5.8, there's a very interesting question how to do this. And that's proposition 8.5. Proposition 8.5 says if I have two specializations, then the first one really specializes to the last one. And now there are two proofs of that, and I give you an exercise. Proof 8.5. And it's very interesting. There are two proofs. If you want to apply 8.5 to the situation we are here, it is just easy because you have existence of modular spaces. You see? What does 7.1 say? 7.1 says that any point is in the closure of the A equals 1 part. What does 5.8 say? That any A equal 1 point is in the closure of the interior of the Newton polygon strata W beta D. So if you close up W beta D, it contains this stratum, but it also contains the closure of this stratum. So it contains this point, and that's exactly what you want. Now, if you don't have modular spaces, it's really interesting to write this out. And you will see that, I mean, I just follow your nose, like we say in Dutch. You just do what you have to do. I mean, you write out that one specialization exists over some base, then you have another specialization existing over the fraction field of that ring, and then you have to invent a new ring over which you can write such, of which you can write out such a deformation. So as an exercise, I give you the following thing. So, and that's perhaps very nice. So the basic proof of 8.5 is 8.5 rests on the following observation. You have a ring deforming your original thing, but you also have a closed point. Then you have a field of fractions, right? And that sits in a new ring, and that sits in a field of fractions, and this also has a rational point. So this is writing out a deformation, and now all the things I have are schemes over the spectrum of R, schemes over the spectrum of B, having the property, the generic point, the special point, and so on and so on and so on, right? And now all you have to do is find a new ring which sits in here such that the field of fractions of gamma is equal to this, and that this has a closed point here. And then you make a scheme over gamma such that the generic fiber is the one you have here, and the special fiber is the one you have there. Now there's an obvious choice for this. Namely, you take in gamma, you take all elements in P such that, what is F? This is F, such that F of Y lands in R. Yes. Now, of course, this does have a map to K, right? So this map H here is this map H here. But I like you to compute through this ring in very special cases. And for example, there's no chance that this gamma is Noetherian. There's no chance that this is an Agatha ring or anything like that. It's really a beautiful thing. And it's very fun to describe all maximal ideals and so on. It's really fun. I played around with it. So that's another proof of 8.5. And I think you like my first proof much better than my second proof. Yeah? Okay, I'm going to spend with you 5 minutes on doing the polarized case, and then I come to the Manning conjecture. Okay, let's try to prove the case 7.1 in the most simple case we know. Well, the one with simple case. I take two elliptic curves. I take the p-divisible group attached to this elliptic curve, and does it have a deformation to A equal 1? Right? Okay, I don't know how to do it, so suppose the E is supersingular, and then I can write out the display for E. I can write as follows. I have a 1 here, I have a minus P here, I have a 0 here, and that's the display for my first curve. Yeah? And then of course I have my display in the same way for my second curve in here. And now it's very easy. You know how to do everything. I mean, this is certainly a symplectic base. So what you have to do is you multiply a symmetric matrix with this, and the deformed thing is something like ST, TU, and then you have the rest, which I'm not going to write down. Yeah? And all I'm interested in is a deformation where the neutral polygon stays constant and where the A number becomes 1. And here you're helped greatly by the fact that you're very low dimensional. Namely, if this is a matrix and moreover the P rank is 0, it is a deformation of something which is dimension 2 and supersingular, but for dimension 2 there are very few Newton polygons. So if this has P rank 0, then it's automatically supersingular. So that helps a lot already. So the condition that this is supersingular is that STTU times S sigma T sigma T sigma U sigma is the zero matrix. Aha! So I have everything under control. Now you write out this product, right? And you get 4 equations. And all the 4 equations you have to equate to 0, and you have to work on it. And I advise you to do the nice exercise. So all solutions are of the following form. They are of the form, you can take one of the variables, say t, you can leave as it is. You have to choose an element zeta in your bit vectors of your algebraically closed field, such that what's my equation? Zeta sigma zeta is -1. I hope you think now, aha, I know if P is non-2, this is a 2P plus 2 root of unity. Yes? P plus 1 is -1, so 2P plus 2 is S plus 1, so this is a 2P plus 2 root of unity. And that's correct in case you're in characteristic non-2. But okay, it doesn't matter so much. And then the matrix is, I take ST TU, I can solve by taking the following equations. The S is sigma T, I leave the T, and I take here sigma inverse T. Sorry, zeta, that's called zeta. Okay, now you just check that this matrix really is the universal solution of my equation here. So what does it mean? Well, first of all, you easily see that this determinant is not 0, right? So the Hasserid matrix has a determinant non-zero, so the rank has dropped, but it certainly is not, it certainly is nilpotent. So now necessarily the A number is 1. So what have I done? As soon as I choose the zeta, I can deform by just a smooth curve to A number 1 by just taking T a variable. Now how many choices do I have for zeta? You see, you know that zeta sigma times zeta is not plus 1. Yeah.
Sorry, I'm confused. What do you mean by applying sigma to
Sigma is an element in W. A sigma is sigma. I'm sorry. Sigma is the lift of Frobenius on W. I'm sorry, I used twice sigma, but the neutral polygon sigma is the supersingular one, and sigma is the lift of Frobenius on my algebraically closed residue field. Thank you for asking. Okay, now if you combine these two, there are P plus 1 solutions. Yeah? So, what does it say? Through my point, I have P plus 1 curves, and on each curve, the A number gets 1, but the neutral polygon stratum is extremely singular. It's an intersection of P plus 1 solutions. And actually what you can prove, and that's in one of my papers, that these p plus 1 directions span the whole tangent space of the moduli space. So that's rather tricky, right? And now you see, you're not going to do this in general. I mean, for an arbitrary Newton polygon, the matrix is much more complicated. You get here a huge Hasselbalch matrix. It's not sufficient to say that the G's power of it is 0, because that only gives you p rank 0, but certainly not a Newton polygon, and so on and so on and so on. So the general case is really a complete mess. But there's an easy escape. Suppose my display was as follows. Suppose this was my display, and suppose and this again is on a symplectic base, and this I multiply by S0, 0, 0. Yeah? And now you see what happens. Now if you multiply this, you get a new display, right? And the only place where you get something is in this corner, and the rest is 0. So all of a sudden, this choice is magical. I mean, this has p plus 1 directions. But here you have only one direction, and that's a nice smooth curve. Okay, so now comes the theory. Instead of taking an arbitrary p-divisible group, you take a filtered p-divisible group, which is symplectic. And you take only deformations of the filtered p-divisible groups, right? And then the old theory just goes through in this case. In this case, you prove this theorem. Now, it's quite mysterious. I mean, so morally, it says that the p plus 1 directions are just the p plus 1 possible choices for a sub p-divisible group, which of course is isomorphic to G11. And that has been studied quite a lot in the paper on stratifications. That appears, but it appears in many cases. Okay, so this is the proof. This is the end of the proof of the analog of the Grothendieck conjecture. I'm not going to say anything more. You just study the notes and you'll see what. It's okay. Is it clear, the two examples, how they are different? In this case, the polarization is just in diagonal form, and this case, the polarization is certainly not diagonal form. Okay, now I'm going for you back, as my last topic, I'm going back to Manin's conjecture. So what is Manin's conjecture? You give yourself a symmetric Newton polygon, and you try to find an Abelian variety with that Newton polygon. And I'm going over with you again on the second proof, but being much more careful. And I hope that you're very critical in the sense, what is the main point? The main point is we can construct Newton, for a Newton polygon, we can construct p-divisible groups. What do? You just take everything Ching-Lee told us, right? That a GMN and the product of GMNs give you a p-divisible group, and you know exactly what to do. So I want to tell you, constructing p-divisible groups is easy, right? Studying isogenous p-divisible groups is quite something else, but construct them is quite easy. So what Manin's conjecture says, okay, I construct any p-divisible group with Newton polygon psi, show it is a Newton polygon of an Abelian variety, and actually easily prove that once the Manin's conjecture is proved, all p-divisible groups attached to psi appear as p-divisible groups of some Abelian variety. Proof. One appears as an Abelian variety. I have an isogenous of the given one to this one, and this isogeny you can lift to the Abelian variety, and you're done. So once you have one Abelian variety with this psi, all p-divisible groups with psi do appear, right? But the point is you only have to choose one. Okay, now here are my steps in my proof, and you should be very non-believing first. Because what I do, I first construct a p-divisible group which is supersingular, principally polarized, and has a number 1. And that should be easy, and I'll do that for you in a minute. Okay. So that's the first thing I'm going to construct for you. And the second thing is that I'm going to solve the Mannian conjecture for supersingular being varieties, but in such a way that I really have this Newton polygon. So you kind of think that I'm doing a circular reasoning, but that's not true. The second step I will analyze, but you see, any supersingular being variety is any supersingular p-divisible group is isogynous to a product of supersingular one-dimensional formal groups, and those come from elliptic curves. So up to isogeny, you can easily construct lambda, and you just have to take care that you have the root thing. So this proves the Mannian conjecture for the supersingular case, but that's kind of automatic. So deep reason behind this, you know how to solve the Mannian conjecture for G11, hence you can solve for any supersingular one, right? Then there does exist a deformation of this such that a given Newton polygon is achieved. And that's just my principally polarized version of Grothendieck conjecture. And then you're done. Because if you have this deformation, and mind, this is the p-divisible group of the Offenbeing variety with polarization, then by certate, you have a formal principally polarized being variety whose p-divisible group is just the deformation we had. That's just certate. Okay, and now you use what we call Chow-Grothendieck, or you use Gaga, or whatever you want to call it. The classical Chow theorem is that if you have a complex variety, which need not be algebraic at all, and you can embed it in projective space, then it's algebraizable. That is the sense, that's to say, the underlying space is an algebraic variety, and the one you had was just a complex structure on that algebraic variety. Okay, now how do you use this? If you have a complex torus, and you have a very ample line bundle on it, then this very ample line bundle embeds your torus into a projective space. And by Chow, you get an algebraic variety, and that necessarily is an abelian variety. Now Grothendieck generalized this in his EGA, saying that if you have a formal abelian scheme, and you have any polarization on it, then this is algebraizable in the sense that there does exist an abelian scheme over the spec of R, which if you formally complete this, you get the old thing back. Okay, so this is just a matter of technique. So now you see the whole setup of the theory. We start with a starting point, which is a supersingular one, which is principally polarized, right? That is algebraizable. Then I deform, and then by certate and by Chow-Grothendieck, we automatically get an abelian variety. So the only thing I have to do for you is to construct one, and the rest is just blah, blah, blah. It's just general technique. And now let me show you how to do this. There are many ways. One is that you refer to the lecture notes by Keizang Li and myself, and the basic, the central theorem in the whole lecture notes is that every component of the supersingular locus has this as dense subset. But that's non-trivial. And actually one difficulty in our whole proof was that we really have to cope with problems like this, and that you really have to cope with filtered definitions and non-filtered definitions. And you see, if I choose a filtration that sorts out one direction, but the other p directions are impossible for this filter definition. So that's in the background of this lecture notes with Keizang Li and myself. But let me give you a much easier proof. I just start by a matrix in this plate form, and the rest is 0. And I wonder what kind of matrix is this. So this is the matrix of F. Yeah? Now it's clear that if you do F to the power 2G, right, what do you get? Well, the first G steps, you get 1, and then each next step you get plus P, except the last step you get minus P. So this, applied to E1, gives 0. So my Cayley-Hamilton technique is here one of the most trivial ones, right? The E1 is annihilated by F to the 2G minus P to the G. And now from this equation, you can immediately read off the Newton polygon. Namely, the Newton polygon is just the p-adic values of this, of the zeros of this equation, and they're all a half. So here the Newton polygon is a half. 2G times, so that's what you call sigma. Yeah? And now I have to put a bilinear form on it, and that's obvious how you do it. You just make a symplectic base like this, and you prove that that is a symplectic base, right? So then you know that this is a principally polarized. So this solves 1. Yeah? And as soon as I've solved 1, I'm really done. So now in order to prove 2, you take your x0 here, and you take y0, which is just g11 to the power g. You choose an isogeny, right? And this one is equal to the p-divisible group of e to the g, p infinity. Yeah? And this kernel sits also in here. And I can take the kernel, so that sits in e to the power g, and I can take e to the g mod n, right? And of course this equals this. Now, I have a principal polarization here, so I can pull back a two polarization here, so the lambda 0 pulls back to mu 0 here, right? And now I choose rho 0, which is this polarization. Now to be careful a little bit, I might involve also factors prime to p. But if I get factors prime to p, I just divide it out. So I can assume that the degree of rho 0 is the degree of mu 0. And then that implies that this descends to a lambda 0, which is isomorphic, and which is the old lambda 0. So that solves 2, and that solves everything. Okay, so that's a close analysis of the whole proof of the Manning conjecture. And I hope you see how this deformation theory really helps us a lot in improving all these things. Now, I've only 3 remarks to make to end this talk. Besides that, I hope that you liked the material. I would like to thank the organizers for this wonderful workshop. I've enjoyed it very much. I really think this is a fantastic thing. But I even would like to thank more the participants, because I've talked to a lot of you, and all talks were extremely interesting, and I'm really, well, I'm proud of having such good students in my audience, and I hope that you do very well in the research. That's my second remark. And my third is that I want to thank Ching Li for all the cooperation. Okay, thank you very much.